All right. Now, the announcements I wanted to make, let me get this up. One is no real consequence to this class unless you happen to be looking for me, okay? Next Tuesday, I have a doctor's appointment at 10 o'clock. I know this is a Monday, Wednesday class. You're probably not over here on Tuesday. One is. But it's a 10 o'clock appointment, but I've got to go in for blood work at 9. And that means if I came to campus, I'd have to leave by 8:15 to get back to the Kirkland Clinic to be there by 9 and be parked and be there for the blood work. So I won't be coming in at all. Normally I have class. 2 classes are wiped out, and I've made arrangements for both classes. We're going to make up one, and they're going to YouTube on the other. So, but if you were looking for me that day, early in the morning or something, I'm not going to be here until probably around 11, and I have a class then too. So I still won't be available until 12:15 at the earliest for office hour type stuff. So that was the one that's sort of not very important because y'all are Monday, Wednesday class. But the other one is important, and I wanted y'all, well, let me do this first. I finally got everything out there on Blackboard. Okay, I think it's totally set up now. I corrected your syllabus and got it out there. I corrected the research paper instructions. It's out there. I've got the corrected copy of the my locator card there. I have the files, the PowerPoints for every chapter that we'll do any part of out there. And I've got the websites that either students have given me or I found myself that I thought may or might not be useful to you. They're out there. And the link for the YouTube videos. It's out there all under content in Blackboard. I'm trying to think. Let's see. No, I don't have any scores out there because no one's turned in a paper yet. But don't forget your papers. Okay. But anyway, everything's set up now on Blackboard for this class. Neither one of you are in differential equations. So I don't have that one finished. I have it started, but not all of it done. And then my physical science class, I have most of it done, but I don't have the grades in there yet. They have turned in work. Okay. Now, the other thing, and this is the important one. We have a math team. We just started it last year, and we had a really good time with it. Students, sort of got pretty fired up about it. They actually did quite well in the first ever competition they went to, and we're going again early October. It's either the first or second Friday in October. There will be a math competition at Shelton State in Tuscaloosa. And since you are a student, you certainly could participate if you would choose to, okay? And one, you definitely can participate when you choose to, okay? So it's fun. We'll start having practice sessions maybe as early as today at 3:15, but Miss Nyla Geraci is the coach for it, but I help out too, especially for students on this campus. But she can come to this campus too. I have so few office hours. In fact, Monday, Wednesday afternoon, 3:15 to 5:15 is all I got right now. And the one student that wanted to do it from yesterday's class, linear algebra, said she was available 3:15 to 4:45. We won't necessarily go an hour and a half every day. We may not do it every day, but and I don't even have any of the questions yet, but I'm hoping Dr. Thomas has some that we can start reviewing some of the past questions to see what types of things and approaches to how about doing this. So either one of you interested? It really is fun, and you really get to know math a little bit better, and it's fun. I mean, to figure out easier ways to do problems, quicker ways, that kind of stuff.
I mean, I would like to, but like my work schedule doesn't work. It's like
I don't, especially with the I don't know.
Yeah, I was going to say. Yeah. Have you all already started practicing or working out or whatever?
Yeah, I'll start
Tomorrow. Yeah. Okay. All righty. Well, okay. Worth a shot, though. You would be the prime candidates for it, so I just wanted to run it by you. Okay, so let's get on to where we left off last time. Any questions on anything we've done up till now? All right. Example 10 is calculate the area under the graph of this curve. Y is equal to, I'll go on and blow it up here. I'll have to reduce it as soon as we get talking about it. This curve here, y is equal to x over x squared plus 1 between 1 and 3. The area under that curve. How would you calculate that? I'll get my pen set up. What? How do you calculate area under a curve? Okay. In Cal 1, and in differential equations, a lot of those things, sort of like, I don't want to get too much into things, but at several churches I've attended, they have what they call children's church. All the kids go up front, either a pastor or somebody goes up and they have a little church, and then they send them off to do something other. Usually they start with a question. And sometimes it may be a little bit of tough questions. All the kids sitting there don't know what to say. Always one kid will sort of say, Jesus? Yeah. That seems to be a safe answer at any time, at church, to answer Jesus. Okay. Well, in Cal 2, the safe answer is integrate. In Cal 1, it was take a derivative. In Cal 2, it's take an integral. Okay. So how do you reckon we're going to get the area under a curve? Integrate. All right. Glad y'all saw that so easily. Okay. And what would you integrate? Okay. Integral. I did that. What goes on this? 1 to 3. Okay. X over x squared plus 1. Second? dx. Okay? Now, here's what you should, I shouldn't be telling you what to think, but what you're doing here is imagine that you break this into a bunch of dx's. That's what the dx is there. Little increments of that, delta x's, right? And every one of those then represents a little rectangle there, right? The delta x is the width. The height is the function, x over x squared plus 1. That's the height. There's the width. And you're summing all those little things together. That's an integral. So your height is x over x squared plus 1. That's what the y value is. Your width is the dx. Okay? And you're summing all those, you're integrating those between 1 and 3. That's what an integral does. That's what you think. How do you do that integral? Second? Okay, and do you know what antiderivative that would be? That looks pretty familiar. That's one of our common ones, isn't it?
X squared over 2.
Okay. Another thing might be to look at the title of the section we're on. Say again? Okay, the title of this section, 5.7. What is it? Substitution method. Does that give us a hint? Oh yeah, let's use something to substitute. What might we use? Oh, I know it was at least a week ago that we met, so long time, holiday weekend. Oh yeah. Let u equal
X squared plus 1.
Very good. X squared plus 1. The most complicated part, the innermost part of the most complicated part of your problem. And that's your denominator. Then, du is equal to? Say again? x is in there.
2x.
2x dx. Very good. Okay. Okay. Now, we don't have a 2x dx. We have an x dx. So what can we do here? Divide by 2. Now we have an x dx, but now we have a du over 2. All right, so if we do this substitution, what does that give us? One half, get that out in front. The integral, okay. What do we put there, though? Because ultimately we're going to have a du over here. That means our limits need to be what u are. These limits are what your x are. X is. Okay. Say again? Okay, wait. Before we do that, I want what to put by the integral sign. Do I put the 1 and 3? The 1 and 3 correspond to x's. We want u's. We want u. No. Yeah, I know it was a long time ago. A lot of barbecues. Oh, by the way, the coach for the math team, this may get you to become Mr. Racing.
So,
And she had a few choice words about no. Okay.
so it will be 2.
Okay. The lower limit will be 2. How did you get that?
Because you plug it into the
Yeah, plug it in for x. 1 in for x, that would be 1 squared plus 1, that's 2. And then the upper limit would be 10. Okay, very good. 3 squared plus 1 is 9 plus 1 is 10. And then what do we have here? The du is the 1/2 x dx, so this part went into our du, 1/2 du. And what do we have left? 1 over u du. Can we integrate that? Yes, it certainly is the ln. ln u evaluated, evaluated from 2 to 10. Okay, and that will be 1/2 log of Second? You may have said it right, I can't hear well. Just plug in. One-half log of, plug in the 10 for the u, log 10 minus log 2, right? That's a pain in the neck, okay? Now, we can use some of the principles of logarithms to sort of make this work a little bit better. That would be 1/2. Do you remember what the difference of two logs? The difference of two logs is the same as the log of the don't remember, let's see, is it in front of the book or the back of the book? Exponents. What would you say? Yes, exactly. The log of 10 over 2. That's exactly it. Okay? And this would be 1/2 the log of 5. Okay? And you could rewrite that even another way. And what would you do that? No, the log of 5 to the 1/2 power. In other words, the log of the square root of 5. And if you got a handy dandy calculator, you can actually figure out what that is. Second?
804.
Okay, they rounded to approximately 0.805. They rounded to that. Okay. All right. Make sense? Okay. Now, actually, yours may be more correct than theirs because they did 1/2 log 10 minus 1/2 log 2, which is fine, but when you subtract numbers like that, you sometimes lose some precision. Whereas you carry it all the way out, then you're going to have the maximum precision. So yours is probably a more correct answer than theirs. Okay. Good deal. Any question on that? I feel like a dentist pulling teeth here. Okay. Does that make sense? All right. Now, they have a little summary here. That's one thing Ms. Martin liked about this text. They always summarize at the end of each section. But then the thing that some classes find useful, on the exercises, they have some preliminary questions. Would you find it useful to do those or not? It's up to you. Would that be a good little review of what we did, or it's just rehashing it all and you already know it? Review it? Okay. So let's do, I'll go on and clear the screen if that's okay. All right. I'll just write on this screen. Which of the following integrals is a candidate for the substitution method? Well, here's the first. The integral of 5x to the 4th sine x to the 5th dx. The B one is the integral of sine to the 5th x cosine x dx. And the third one is the integral of x to the 5th sine x dx. Okay? Says which of the following is a candidate for the substitution method? What you think? First one? Yeah, that looks like a good choice to me, because let u equal x to the 5th, du would be 5x 4th to the dx. Yes, that would be a great substitution. How about the second one? Yeah, sounds good to me too. Let you, what would be your u? U equal 5. Du would be 0. Okay, that would be real helpful with it. Second? Okay. That's ultimately what it's going to become. You're thinking ahead really well, but your substitution let you, the innermost part of your most complicated part, most complicated part is the 5th. The innermost part of that is sine. Let u equal sine x. Then du is cosine x dx. There's your du. This would be u to the 5th du. Yes, that would be a great possibility. How about this one? No. Substitution method will not help you at all with that. Later we'll have a method that will, called, a technique they actually call it, integration by parts. That's coming up. We'll get there. So they do have answers in the back for the preliminary questions generally, and this was 5 point something another, 5.7. Okay. .7 A and B, you got it right. Good deal. Okay. Number 2. Find an appropriate choice for you for evaluating the following integrals by substitution. Can I go on and erase this one? Okay. The A here. Integral of x times x squared plus 9 to the 4th power dx. What would be your u? X squared plus 9. Perfect. Everybody agree? Good deal. The B one is the integral of x squared sine x cubed dx. Second, let u equal what? Really? Okay. Then du would be, boy, a chain rule, that would be cosine x cubed times 3x squared. Do you see that anywhere up there? No. Keep it simple. X cubed. Let u equal x cubed. Okay? Then du would be 3x squared dx. You got an x squared dx. You can deal with the 1/3, right? So yeah, that's my x there. My u there. Okay? How about this one? C. The integral of sine x cosine squared x dx. What would be your u? Let u equal what? Cosine x. No, not cosine squared. Cosine x. Okay, why? The innermost part of the most complicated part. The most complicated part is cosine squared. The innermost part of that is cosine. What would your du be then? Minus sine x dx. There's your sine x dx. Yeah. And then you have u squared du with a minus out front. Yeah, we can handle that, right? So, you see how it works? Let's see if they got it right in the back. Sometimes they miss it, but let's see if they got it right. 5, 7. The first one, the A would be x squared plus 9, good for them. The second one would be x cubed, good for them. Third one would be cosine x, great for them. Okay? Number 3. Which of the following, let's go and erase this, is that okay? All right. This is Wednesday. That's good. Okay. I want to make sure, especially Irma or what's her name? Irma. She looked pretty bad. Most powerful Atlantic hurricane on record. Oh, really? Oh, man. Oh, man. All right. And what's that name? The second one? Jose. Okay. Yeah. All right. Number 3. Which of the following is equal to the integral from 0 to 2 x squared times x cubed plus 1 dx for a suitable substitution? Here's the A part. 1/3 the integral from 0 to 2 of u du. B part, integral from 0 to 9 of u du. The C, possibility, 1/3 the integral from 1 to 9 of u du. Okay, those are my only 3 options. Look like u du wins as the integrand. So that's the only option we have. But which of these would be the result of the substitution of the first Do as much as you need to get there. Where would you begin? Okay, let u equal what? X cubed plus 1. Good. Then du would be 3x squared. One more. Something else. Dx. Okay, very good. All right. Now, from that, you don't. Second. Second. A little louder. I can't hear. You say B?
C.
C. Okay. Definitely you're going to have a 1/3 because you got to divide by that because you don't have a 3x squared, you have an x squared dx. You're going to have a 1/3. So that means it's either going to be A or C. What's wrong with A? All right, the limits are not right. Those are the limits for x, not the limits for 2. If you plug in, for u, if you plug in for x, that would be 1 to 9. Sure enough, C is wrong. Way to go. Let's make sure the back of the book got it right too. C. That means yes in Spanish. Okay. So they got it right. All right. Homework exercises then. Any of the odds 1 through 5. And any of the odds 7 through 23. Either 27 or 25 or 27, or both if you choose. And then any of the odds 29 through 73. Just a few to choose from there. And then I would say do some of the odds, any of the odds 75 through 79. And then do any of the odds 81, through 95. Then do 99. It's the only one like that. By the way, there's a Rayleigh distribution. I think we mentioned that last time, didn't we? Okay. Or some earlier time. If you want to write on who in the world Rayleigh is, that kind of stuff. And then any of the odds 101, either 101 or 103 or both. Okay? And then I would try to do number 105. All right. If you want to look at any of the more complicated ones, you certainly can. Further insights and challenges, you're not required to. All right. Any questions? 5-7. Okay, let's move on to 5-8 then. All right. Now, we're not going to do a lot with this, but we're going to do some. No, we won't do all of it, but we'll do some. Because some of it we've already been doing. Okay. Good deal. Finally. All right. Back in section 5.4, which we went through pretty quickly, the fundamental theorem of calculus part 1, basically we ran by this real quickly. Let me get my pen back. Okay. That the integral from a to b of dx over x, that could be written as 1 over x dx also. What would that be? That's the ln of x evaluated from a to b, which would then be, second, ln of b minus ln of a, which would be, another way to write that, b over a. You got it. Okay? We just did one like that, so what's new here? All right, now, here is a way that you can calculate then any log x, okay? It's actually doing an integration. Well, here it is right here. Basically, what we do, since this is going to be your answer is ln b over a. Okay? If you want ln x, obviously you want the a to be 1, right? So you have the lower integral be 1. Okay? The upper integral, you want it ln x, not ln b, so let x equal b. So the upper part is going to be your x. Well, now that that's going to be the x, you have to change the integrand to be not x in it, but some dummy variable, like t. Okay? So you could do ln x then, that would be from there, is equal to the integral from 1 to x of dt over t. That's good for all x's greater than 0. Why do they have to be greater than 0? You cannot take the log of 0, and you can't take the log of a negative number. So this is good for any of them. Now, if that x is between 0 and 1, then the number up here is less than this one, so that's going to be a negative integral. And the log of the number between 0 and 1 is negative. Okay? So yeah, that makes sense. If it's equal to 1, then x equal 1, that's going to be 0. And the log of 1 is 0. Okay? And for any x is greater than 1, this will give you that. So yeah, that works for any x's greater than 0. If they're less than 1, it's going to be negative. Equal to 1, it's going to be 0. Greater than 1, they're going to be positive. So that's kind of doing the fundamental theorem of calculus part 2 for the log function. Okay? Now, in a similar way, you can do things like, oh, and here's the illustration of that. I was looking at it in the book and not thinking, but that's exactly what the area under the curve here is, that value for log x, whatever value x is. If x is back here, that's a negative because you're going from 1 to x, that would be the negative. Anything to the right would be positive. If x is equal to 1, the area under it is 0. So that gives you log x. That's one way to calculate log x. If you didn't have a table, but you happen to have an integration, you could do, which that would be harder than a table. Okay, or your calculator. Now, similarly, we can do this. Okay? The inverse sine of x would be the integral of the derivative of the inverse sine of x, right? Because the derivative undoes the integral. This is fundamental theorem of calculus part 2, basically. And this would give you, because this is the derivative of that. So the integral of the derivative will give you this, as long as this is here. Now, you start this one at 0, which will be fine. But this is only good for x's between -1 and 1. Part of the reason is your inverse sine is only defined from -1 to 1. But it includes -1 and 1. You can't include the -1 and 1 here, because if you did those, you would have 0 in the denominator here, which you cannot have. So, you have to exclude the equality effect. Okay? Now, you can do this for any function, basically. If you know the derivative of a function, you can evaluate that function, whatever it is, by putting the integral of its derivative. Okay? Because that's what this fundamental theorem of calculus part 2 tells you. The integration undoes a derivative. Derivative undoes an integration. Okay? So, it's nothing that I would really get too wiped out about, you know, but that is a way, I mean, that's reality. So all of your, okay, and here's the illustration of that. this is that function, y is equal to the square root of 1 over the square root of 1 minus t squared. If you were to do that, then the integral of this function between minus 1 and 1, not including this, because that's going to infinity, that's going to infinity. Can't have that, okay? But anything inside of minus 1 and inside of 1, then this would work. And again, if x were over here, that would give you a negative value, over here a positive value, equal to 0 would give you 0, and all that fits. So that area is your inverse sign, because the derivative of inverse sign is that thing. The integral of a derivative is the function within limits. Okay. Now, here are your other inverse trigonometric functions. Okay. Now, this is perhaps where I wouldn't make a very good pure mathematician. I'm not even sure they would, but I'm not going to sit down and memorize these things. No. Okay? If you ever need them, look them up. Okay? Y'all are both going in engineering, right? Civil, right? Guess what? When you do your EIT, your professional engineering exam, and those kind of things, you can carry with you. I don't know what they do in the computer age, whether you're a calculator that has all of it in it or tables. They don't expect you to memorize these things. Take with you what you need. Okay, you'll get alerted to all that. But anyway, this is derivative, and then that would be the integral. So you see, the integral undoes the derivative. Derivative of this is that. When you integrate this, you get this. Integrate this, that's what you have. Okay. Plus c. Remember, indefinite integral, you always have to have the plus c. Okay. Inverse tangent, inverse secant. Now they don't do cosine, cotangent, cosecant, because there's very little difference. If you ever need one of these, basically it's going to be one of these two. Very seldom have I ever needed this, except to do it now. Okay, but and seldom we need the others, but in case you do, there they are. Okay, like I said, we're not going to do a lot with this. I just want you to be exposed to it. Okay. Here is the illustration for example 1. This is y is equal to the integral, the function here is y is equal to 1 over x squared plus 1. That's the graph of it. Okay? Now, how would you calculate the area? They tell you what it is, but how would you calculate it? Yeah, like an integral of it. And when you integrate that, because this happens to be the derivative of the inverse tangent function, then that gives you exactly that. So that's good to remember. Make a good kid at first. No, okay. All right. Now, I can't remember if we've done this before or not. But these are integrals involving f of x equal b to the x. Okay? Now, they skipped example 2 and 3. That's using substitution. Okay. I guess we ought to go back and do those, because you may run into them. I was just going to skip them, but let's do them on this one. Here's example 2. The integral that we have, we don't even have a graph for it. From 1 over root 2 to 1 of dx over x times the square root of 4x squared minus 1. Okay. Now, the main reason I wanted to do this one is if that x that you see right here had been up in the numerator, this is a piece of cake with substitution, right? You let u be the part in here, it goes from there. Right? However, it's down in the denominator. Oh, what a pain. Okay? So obviously you can't do a regular substitution with this one. But what you might do is recognize that's awfully close to an inverse secant. Okay? Secant has that x in front and the square root and thing in the bottom of the derivative of the inverse secant. But it's not quite. Okay? And that's where it says you need a substitution. So what you want to do is let u equal the inside of this, 4x squared. Okay, most complicated part of that. Then, what's your du? I don't think my substitution is going to work, because we still wind up with the same thing. Okay, back up. Okay. Like I was saying before, this looks pretty close to being what an inverse secant is. What's the problem with it is that 4x squared. Now what you can do with that is notice that that is the square root. I'm just going to rewrite this. That'd be 2x squared minus 1. Right? 4x squared is 2x squared. Let that be your substitution. Let u equal 2x. Then du is equal to second? No, it isn't. U is equal to 2x. Du would be? No. Derivative of 2x would be 2 dx. Okay. Right? Alright. 2 dx. Like pulling teeth here. We don't have a 2 dx. We have a dx, so we'll divide both sides by 2. And now we have du of 2. Okay, so what we have now is the integral, 1/2 the integral, because that 1/2 comes out. The 1/2 du is dx, so the du goes up here. And since we're using u, what becomes of our limits? What will they be going from? What will be the lower limit? 2 over root 2. And your upper limit? 2. Okay. Now, your denominator, oh, what a pain. Okay, because your u is equal to 2x, that implies that u over 2 is equal to x. All right, we put a u over 2 down here, except I don't want that 2 there. So I'm going to take that 1 over 1/2, which is 2, right? And we'll move it up top, and it wipes that out. So that leaves us just a u down here. I've got to get my eraser back. So that leaves us just a u. Okay. Times the square root of u squared minus 1. Right? Now that is and that U is hanging too high there, that is your inverse secant formula. That's exactly it. So this would be the inverse secant of, from the thing up above, that would be inverse secant of U evaluated from 2 over root 2 to 2. All right. Now, how would you proceed with that? Second? Inverse secant of 2 minus the inverse secant of 2 over root 2. Okay. Now, frankly, I don't know any of those right off the top of my head. And what's even worse, I don't know a calculator that will calculate any of those, because you don't usually have inverse secants there. What we do have are inverse cosines. So what I'm going to say is, let's see, they may just leave it like that. Okay. Well, actually, I should know. Okay. Let's draw the diagram. This is some angle. What do you want to name that angle? See. Second? Second? A? How about alpha? Call alpha. No, okay. Let's call that alpha. Okay. So that implies, this thing right here implies that the secant of some angle alpha is equal to 2, right? Now, again, I don't know my secants too well. But what I do know, what is secant? 1 over cosine. 1 over cosine alpha is equal to 2, which means that cosine alpha is equal to 1/2. Now, do you know that alpha? What? Pi over 6? Is that what you said? Or did you say pi over 3? No. Okay, I think you're right. Sine of pi 6 is 1/2. Cosine of pi thirds is 1/2. So I think it is pi over 3. Okay? So that's that alpha. So this is pi thirds. Okay? Let's do the same thing here. You want to name it a different angle? Beta. All right, very creative. Now that suggests if beta is equal to inverse secant of 2 over root 2, that suggests that one step up, yeah, secant of beta is equal to 2 over root 2. Take it one step at a time, which for this would be cosine 1 over cosine beta, that's what secant is, right, is 2 over root 2. And that would suggest that cosine beta is equal to second square root of 2 over 2. Do you know what beta that could be? Pi fourths. So that would be pi thirds minus pi fourths. Okay, I can't write my pi's too well. And that's your answer. Now, actually, if you wanted to do a little bit more, that would be 4 pi twelfths minus 3 pi twelfths. Isn't that? And that would be pi twelfths. And then you can divide that out and see what you get there. No, they don't. They just leave it as pi-12s. So, actually there, you did need to do a little substitution here because that wasn't purely a secant, okay? Well, actually it turns out it is, but you have to do that substitution to get there. You do one part of it is your 1/2 out front, the other part is your 1/2 in the denominator, which is 2, and they wipe each other out, and you still get that, but in that form, once you've done your, and that's where the limits of your substitution are really important. That allowed you to take it there. Now that's a fairly complicated type example, but when you break it down, how do you eat a 5,000-pound elephant? One bite at a time. So how do you solve these complicated problems? Break it down into simpler pieces and chew up each piece until you're ready for the next one. Okay? Now, that was that one. Let's see, is example 3 going to be, yeah, it's going to be a similar type thing. Can I erase this or? Y'all got it? Okay. So let's do example 3. Evaluate this one. The integral from 0 to 3/4 of dx over the square root of 9 minus 16x squared. Okay? Now again, our usual substitution is not going to work here because you would have to have an x dx in the numerator. You don't have it. So this then lends itself to a trig substitution. And the trig substitution that's going to work here is your inverse sine. Okay? But that's not in the form of an inverse sine. That needs to be 1 over, 1 minus u squared is what we're trying to get to. So, actually, that I think is the way to go. I think. Let's try that. I'm real tempted to say what we want is for first thing we want is that to be a 1 out front, right? So the first thing we're going to do is divide this by 9 and that by 9. Okay, we divided the inside by 9, really the square root of 9, so we have to multiply the outside by the square root of 9, which is 3. You see that's an equivalent thing? We want this to be a 1, so it'll look like our inverse sine, right? So to get that to be a 1, you have to divide by 9. If you divide by 9, you change the problem. I mean, square root of 9, because it's all in the right. So to keep from changing the problem, you have to multiply by 9 too, or square root of 9. Square root of 9 is 3. So this, if you did this, you would get right back where you started. But we don't want to do this. We don't know that's why we did it. So this would then be the integral, and we haven't changed anything, no substitution yet, 3/4 dx hasn't changed, and this would be, I'm going to bring the 1/3 out front, and this would then be the square root of 1 minus 16x squared over 9, right? Do you buy that? Okay. Now, that doesn't quite look like our trig substitution yet. What we need is that last part there to be a u squared. So we want let u equal the square root of that thing. And that would be what? 4x over 3. Right? Then you do the next part. Second, du is equal to 4/3 dx. Okay, y'all are good. All right, but we don't want 4/3 dx. We want dx. So what will we have to do? Actually, I don't want to divide by 4/3. Normally I would, but there's an easier way, is multiplying by what? 3/4. And this wipes that out. So now we got that. The 3/4, the 3's are going to go out, and that leaves us with the integral, well, 1/4, the integral. This will be a du here. And what would be underneath? The square root of 1 minus u squared, right? If u is equal to that, u squared is equal to 16x squared over 9. So there's your u squared. Okay. What have I left off? What are we missing?
Limits.
The limits. So what are our limits? 0 to second. Okay. Here's what we're doing. What this says is x equals 0 to x equals 3/4, right? So if x is equal to 0, u is equal to 0. If x is equal to 3/4, 4/3, then 3/4 is 1. So the new limit is 1. See it? Okay. Now, this will be 1/4. What's the antiderivative of 1 over square root of 1 minus u squared? From the table up above. Oh, you don't have that handy? Inverse sine of u, right? And that's evaluated from 0 to 1. Okay, so this will be 1/4 inverse sine of 1 minus inverse sine of 0. Does anyone know what the inverse sine of 1 is? Oh boy, pulling the old black box. Slows you down. Pi over 2, of course, okay, because the sine of pi over 2 is 1. This is pi halves minus, what's the inverse sine of 0? Oh, punch, punch, punch. 0, okay. So 1/2 of pi over 2 is? Pi, right? See it? Good deal. And that's what the book had. Good for them. All right. I thought I needed to show a couple of those. If you have it in a form that looks like it's going to be a trig inverse trig substitution, you got to get it into the pure form, and that's where your u's come in. Not the way we used to do. You take the innermost part, but you get what you want it to be. And in order to get that, you had to manipulate this for a while, so you got that. That's what you want to be u squared. So the square root of that is what you use. So it's a little bit of a deviation of our normal substitution, because you're trying to get it into inverse trig form, or one of the other forms. Okay. Now, that leads then to how you do something like this. And I'm pretty sure we've done this before, haven't we? It's just, I teach Cal 1, Cal 2, and Cal 3, and I can't remember which I've done and which. And maybe we do need to back off and actually, let's start with the function. Let y equal b to the x. Okay? Now, do you remember how to take a derivative of b to the x? D of b to the x dx. I'll tell you this part. Don't say x times b to the x minus 1. Now, that worked if b was your variable and x was a integer or any number, that would work fine. But you see, b is your number and x is a variable, so you can't use the power rule on an exponential. Okay. Now, here's what you do if you're trying to do that. Okay? Start with taking the log of both sides. The log of y is equal to, what would that be? Pretty simple. Just take the log of both sides. Log of b to the x. Is that too sneaky? No, pretty straightforward, right? But now we can use our rule for logarithms. This will give us that log y is equal to, remember that one? X times the log of b. Remember that? Okay. I know they have a bunch of these in the front. Here's laws of exponents. But they don't do logs here. Trigonometry, trig functions. Why don't they do the LNs and the EXPs? Maybe that's in the back. I don't think it is, but yes, it is. Okay. The back part of your text, those pages at the very end, after the index, then the first says elementary functions, power functions, inverse trigonometric functions, and then the next page says exponential and logarithmic functions. And that's where you have all your log rules there. Okay? We just use one of them here. Okay? Get to know them. All right. Now, what we're wanting to do is derivative of y, right? Derivative of b to the x. So let's do it. Let's do derivative with respect to x of this. And we'll also do derivative with respect to x of that. Okay? What's derivative with respect to x of log y? Derivative of log y? It's a chain rule issue. It's the derivative of a log. 1 over y times dy dx, right? Agreed or not? Okay? And let's do this side. Now, we're doing the derivative with respect to x. B is a number, a constant. So log b is a number, a constant. So that's the number times x. What's the derivative of the number times x? If that was 7x, what's the root of the 7x? 7. So this would be log b, right? Okay. Now, okay, let's multiply both sides. We're looking for this, dy dx, which is this thing here, right? So let's multiply both sides by y. Fine? You okay with that? So this says that d of b to the x dx is equal, what was our y? That is b to the x times log b. Okay? Now, if you'll look at the top of the page there, it says okay, doesn't quite say it, but it comes close to saying it. They just write it so weird. Yeah, it's there. They say log b times b to the x. It is there. Okay? Well, what does that imply? Okay? If you divide both sides by log b, okay, that wipes out. This is b to the x is equal to d by dx of b to the x over log b. Now that's a little bizarre. They did some manipulating, but that's what you got. So, therefore, if you integrate this, you get this up to a constant. Well, wait, I won't do the constant yet. So the integral of b to the x dx is equal to, you take the integral of a derivative, you get b to the x over log b time plus c, some constant c, because indefinite integral. It's a pretty ugly log, isn't it? Okay, so that's how they got this thing right here. So I'll blow that up. I'm sure you wanted to see all that, how they got it, but that's how you get it. Okay. The integral of b to the x dx is b to the x dx. Almost sounds like an e to the x thing, right? So it's b to the x, but the only thing is you have to divide by the log of b. Then you got a plus c. Okay? So let's actually use that. Let me see. No. In example 4. We may use it in example 5 too, but let's use it in example 4. Okay? Here's example 4. Evaluate from 3 to 5 the integrate 7 to the x dx. Okay? I left it on the page for you so you can use it. Say again? It's going to be 7 to the x over log what?
7.
Log 7. Evaluated from 3 to 5. Now what I'm going to do is pull out the 1 over log 7, whatever that is, and then you will have this to be 7 to the 5th minus 7 cubed. Okay? This is a place for your handy-dandy calculator. I'm not going to begin to try to do that one in my head. 7 times 7 times 7 times 7 times 7. No, not today.
60, 46.
Say that again.
16,464.
That's 7 to the 5th.
That's 7 to the 5th minus 7 to the 5th.
Okay, and then divide that by log 7, ln 7.
8,460.8.
That's exactly what they got, 8,460.8. Now, I'm sure that's an approximate. Yeah. And how you can ever get 5 significant digits out of that, I'm not sure, but we'll live with it. Okay? All right, we were able to do that one. That was really straightforward from our formula. So let's do something a little more bizarre. Y'all want to do something bizarre, don't you? Sure, I could tell. Evaluate this. The integral from 0 to pi halves of cosine theta 10 to the sine theta d theta. Yeah, that's what we wanted to do, isn't it? How would you approach that? Because you run into this every day. I mean, right. Never mind. What's that? Let you. I heard a let you, so let's let you. Let u equal the innermost part of the more complicated part of the problem. Well, this isn't very complicated. That's the complicated part. And there's the innermost part of the complicated part, so that's going to be let u equal sine theta. Okay, then, what's our next step? du is equal to cosine theta d theta, right? And that's exactly what we've got here, isn't it? So we can do our substitution here, and that'll be the integral of, there's your du, is cosine theta d theta, and your u is sine theta, so it'd be 10 to the u. What have I left off? The limits. And what are the limits? Theta equals 0. What's sine theta? Sine of 0. Oh, pull out the blue box. 0. Okay. And when theta is equal to pi halves, what's sine of pi halves? 1. Okay, even on the calculator it's 1. Okay. Now, how do we do that? Say again? Yeah, you may be right. I just don't hear well. Okay, how does that go? 10 to the u over log 10. You got it. Evaluated from 0 to 1. And what would that be? No. 10 over log 10, right? Minus 0. I'll do the second part. No, minus, I'm sorry. Oh, I see what you're doing. Minus 1 over log 10. Or you could pull the log 10 out. In fact, let's do that. 1 over log 10 times 10 minus 1. What's 10 minus 1? 9 over log 10. Now you can use your black box. .91. Very good. So, folks, I mean, it's not a, they can make it look sort of complicated, but it really isn't. That's a lot like an e to the x, isn't it? And how the integral of e to the x is e to the x. So the integral of 7 to the x, 10 to the u, whatever it is 10 to the u just divided by log u. That's the only difference from the e function. But you say divided by log e is 1. So it is the same thing. It's divided by log of that base. Okay? And then the value of e turns out to be easy. Okay. Think these preliminary questions are worth doing? Yea or nay? Huh? Yes? Okay, let's take a look. Find b, there it is, such that the integral of 1 to b of dx over x is equal to log 3. That's the A part of the problem. Okay? That's the dx. Ooh, pretty ugly dx, but that's the dx. Okay? How would you do that? Well, it is the antiderivative of dx over x. Okay, so this would be ln x evaluated from 1 to b. And what's that equal to? Log b over 1 if you want to do it. So if log b is equal to log 3, guess what b is equal to? 3. Okay, that was easy. B is equal to 3. Okay? Now, the second part is not equal to log 3, but is equal to 3. Okay? I thought it would be easier doing this way. I don't think it is. Let me erase. Okay. Let's let that stand by itself. Let's rewrite it again. This time we want the integral from 1 to b of dx over x equal 3. Left-hand side, everything proceeds as it did before. That came down to log x evaluated from 1 to b. And you said that's equal to log b, right? And you want that equal to 3. What in the world can b be to make that equal 3? If you want to undo a log, what do we use? It's inverse function. What's the inverse function of a log? That's the derivative of a log. The inverse function of a log. Okay. I don't know if this is helpful or not. Here is the graph of a log function. This is the point 1, 0. The inverse function of that must look something like this, right? Because it has to be, remember? No. This point right here is 0, 1. What function? And see, 1 over x, where you said negative 1 over x. 1 over x would be here, negative 1 over x would be there. And then like this, but you see you can't cross that. This is something else. This doesn't have an asymptote. That just keeps on going. Maybe it's like this. Keeps on increasing. What's that a graph of? something to the 0th is equal to 1. What is it? You feed in a 0, you get back a 1. Exponent. So the ln function, that's the natural log. So what's our natural base of our system? Say again? E to the x. That's what it is. The inverse function of log x is e to the x. So do e to the log b is equal to e to the 3, right? And what's e to log b? They're inverse functions of each other. What would be e to the log b? An inverse undoes it. The other, right? So that would leave you with b. There would be the b. ln of e to the b would be b, and e to the ln of b would be b. It's just like the square root of 4 is, well, the square root of 2 squared is 2. A square root undoes a square. A square undoes a square root. An e undoes a log, and a log undoes an e. So you wind up with b. Okay? And, let's make sure they got them right in the back. This is 5.7. No, 5.8. That's what I'm saying. That's not right. Yeah. B is equal to 3, and B is equal to e to the 3. Okay. Does that make sense? Is that fuzzy? Or is it making sense? Huh? Okay, good deal. All right, let's look at number 2. Let's clear this. Find b, there it is, okay, such that the integral from 0 to b of d to x over 1 plus x squared is equal to pi thirds. Okay? I wasn't going to spend a lot of time on these, but let's just do one of them. Inverse tangent, that's the inverse tangent function. This is inverse tangent of b, right, is equal to pi thirds. Okay? Now, here's how I think of trig functions. A normal trig function, you take a trig function of an angle and you get a number, right? So that means for an inverse, you have to take the inverse of a number to get an angle, right? So that's why I say this is an inverse, so that's going to give me an angle. Give me an angle. Make up a... No. A symbol for an angle. Second? No, a symbol for an angle, a variable. Theta, one of my favorites, okay? What x is for equations, theta is for angles, okay? So this tells you, let's rewrite this in a different way. Rewrite this expression as equivalent expression without an inverse in it. Tangent of theta is equal to b, right? But, okay, here, this theta is obviously pi thirds, right? That's what we were given. So this says the tangent of pi thirds is equal to b. And what is the tangent of pi thirds? Tangent of pi thirds. All right, good old calculator time. Let me put it this way. Say again?
2 over square root.
Yeah. I get
Radical 3? Is that what you said? Yeah. Let's think of it this way. This is the sine of pi thirds over the cosine, right, of pi thirds. Anyone remember what sine of pi thirds is? Root 3 over 2. And cosine of pi thirds, we already had today, was 1/2. Sure enough, that is root 3. All right. Hopefully the back of the book has that too. Number 2 is root 3. Look at that. They got it right. Good for them. Let's look at number 3. You okay with that? All right, number 3. Which integral should be evaluated using substitution? Here's the A one. The integral of 9 dx over 1 plus x squared. And the B one is the integral of dx over 1 plus 9x squared. Which of those two should be evaluated using substitution? Second? Second one, yeah, because you have to do, get that to be a u squared, so the 3x would have to be u. That would be your substitution. Then it's the inverse tangent. This one, just pull the 9 out front, and it's already got that would be an inverse tangent of x. You don't need a substitution at all. So you're absolutely right, the B one. Is that what you were thinking? Of course it was. Okay. So yes, B. Okay. All right, number 4.
I had a 50-50 shot.
What's that?
I had a 50-50 shot.
Oh, I see. Yeah. Okay. Playing the odds. Okay. Number 4. Which relation between x and u yields this? Okay. The square root of 16 plus x squared is equal to 4 times the square root of 1 plus u squared. What is the relationship between x and u that would make that happen? What's that?
What's it asking?
What is the relationship between x and u that would make that true? What relation between x and u makes that true? Well, if you want to do it brute force, you can. If I said solve that for x, or for u, it doesn't matter which, what would you do first? What undoes the square root? Second? Square it. Okay, so let's square both sides. What would this side become? 16 plus x squared is equal to 16 times, right? Okay. So let's multiply through and say 16 plus x squared is equal to 16 plus 16 u squared. Is that right? I'll subtract 16 from both sides. So that gives me x is either is 4u or u is equal to x over 4. Wouldn't it? Take the square root of both of these, that would be x, that would be 4u. Okay. So that's the relationship. I think they probably want it in this form, not that one. But let's see what they had in the back. Huh? Oh, they have x equal 4u. Okay, they had the top. Okay, that's fine. I thought you could say that u equals Good deal. You okay with that? Okay, homework exercises here. Do any of the odds 1 through 9. Do 11. Then do any of the odds 13 through 31. And any of the odds 33 through 69. They don't have enough of those, do they? And then do some of the odds, I'd say either 71 or 73 or both. Actually, those two are both proofs, so if you get too bogged down with it, don't sweat it too much, because I doubt if those answers are in the back anyway. All right, any questions? Okay. Now, 5.9 is a great section. We don't have time for it, though, okay? So I'm not going to spend any, but it's exponential growth and decay. I'm trying to think if in civil engineering, if you do much of this. I don't recall that you do. I mean, you may. I just don't know. So it's well worth a look and a read through, but I'm not going to test you on it. Now, I know y'all are going to be making the big bucks, and you're probably going to be investing with compound interest. That's in this section, so you might want to know that for your own cultural enlightenment, okay? And when you get rich and famous, that's what you need to. And there's also a theorem there on the limit of e and e to the x and continuously compounded interest. That's all there. And then moving backwards, present value. It's all interesting stuff, but we just don't have time for it. So we're going to skip 5.9. Okay? Very much applied things, and if you find it useful, if you're interested in dating, there's isotopes for dating. No, I'm just kidding. Okay. And lots of things you could write paper topics on, too. Next thing we're going to do, and unfortunately it won't be today, we're going to start Chapter 6, Applications of the Integral. Okay? Now, this is a little bizarre how we're doing this. We've done the integral, antiderivatives. Then we did a technique for solving some of those, substitution. Now we're doing absolute applications for the integral. Then we'll come back and do more techniques, and then we'll come back and do more applications using those techniques. So it's sort of like a ping pong match or tennis if you watch a U.S. Open, just back and forth for a bit. But anyway, we'll start next time with Chapter 6. Okay? Any questions? Aren't we out of time? Are we? Yeah. Okay, I thought we were. All my classes start and end at different times, and I don't want to cheat anybody out of a minute of your tuition dollar.